Our understanding of the universe rests on two magnificent pillars, and they cannot both be true. One is quantum mechanics, the rulebook for the impossibly small world of atoms and particles, a realm of probability and ghostly connections. The other is Einstein's theory of general relativity, our masterful description of gravity as the curvature of spacetime itself, governing stars, galaxies, and cosmic expansion. Each is stunningly precise within its own domain, yet they are fundamentally, mathematically incompatible. This is not a minor technical issue. It is the greatest unsolved problem in all of physics, a crack in the very foundation of reality. For over a century, this conflict has driven an epic, expensive, and intellectually furious search for a single theory that can unite them, a so-called theory of everything. By the end of this exploration, you will understand not just the profound nature of this cosmic puzzle, but the startling and beautiful ideas it has forced us to invent, from hidden dimensions to the notion that our reality might be a hologram. What does it mean that our two best descriptions of reality contradict each other so completely? And what kind of universe could possibly resolve such a deep fracture? This first pillar is a world of unsettling magic. Quantum mechanics is the physics of the impossibly small, and it operates on rules that feel utterly alien to our everyday experience. Here, certainty is an illusion. You cannot know both where a particle is and how fast it is moving with perfect precision. Instead, you deal in probabilities, in clouds of potential. An electron is not a tiny marble orbiting a nucleus. It exists as a wave of probability, a shimmer of potential locations, until you look at it and force it to choose a single spot. This is the famous wave-particle duality. Everything from light to atoms behaves as both a wave and a particle depending on how you ask the question. Furthermore, energy in this realm is not a smooth, continuous flow. It comes in tiny, indivisible packets called quanta, hence the name quantum mechanics. This quantization applies to forces as well. The electromagnetic force, for instance, is carried by discrete packets of energy called photons. This framework has given us an astonishingly powerful rulebook for the subatomic world. Its predictions are so precise they border on the supernatural, correctly forecasting the behavior of particles to many decimal places. The crowning achievement of this quantum view is the standard model of particle physics. It is a magnificent, if complex, catalog of the fundamental particles and three of the four fundamental forces: electromagnetism, the strong nuclear force that glues atomic nuclei together, and the weak nuclear force behind radioactive decay. The Standard Model is arguably the most successful scientific theory ever devised. Yet, for all its glory, it contains a glaring, deliberate omission. It has no place for the fourth force, the one that shapes the cosmos on the grandest scales, gravity. In the quantum world, gravity might as well not exist. This is the first pillar, a realm of probability, quanta, and breathtaking precision, but one that is fundamentally incomplete, blind to the force that binds the universe itself. While quantum mechanics reveals a world of chance and fragmentation, the second pillar offers a vision of breathtaking cosmic order. This is Einstein's theory of general relativity, and it completely reimagined the nature of gravity itself. Forget the idea of a mysterious force pulling objects together. Einstein's revolutionary insight was that gravity is not a force at all, but a consequence of geometry. Picture the fabric of the universe not as empty space, but as a dynamic, four-dimensional entity called spacetime, a woven mesh combining the three dimensions of space with the single dimension of time. Now, imagine placing a massive object like our sun onto this mesh. Its mass and energy cause the fabric of spacetime to curve, to warp and stretch like a heavy ball resting on a taut rubber sheet. The motion of planets like Earth is not due to being pulled by an invisible string. Instead, they simply follow the straightest possible path through this curved geometry, a trajectory called a geodesic. Earth orbits the Sun because it is rolling along the curved groove the Sun creates in spacetime. This elegant idea replaced Newton's centuries-old concept of instantaneous action at a distance with a beautiful geometric description. General relativity is deterministic and smooth. If you know the state of the universe at one moment, the equations tell you precisely how it will evolve, with no room for probability or chance. It is a classical theory in the grand tradition of physics, and its predictions have been confirmed with astonishing precision. It explained the subtle wobble in Mercury's orbit that Newtonian gravity could not. It predicted that light would bend as it passed a massive object, a phenomenon called gravitational lensing, first observed during a solar eclipse in 1919, which made Einstein a global celebrity. Its equations pointed directly to the existence of black holes, regions where spacetime curvature becomes so extreme that not even light can escape, and to the dynamic expansion of the entire universe, a discovery that reshaped our cosmic story. Yet, for all its success in describing the cosmos, general relativity harbors a fatal flaw when we look too closely. Its description of spacetime is smooth and continuous, like a calm ocean. But quantum mechanics tells us that everything, including energy and presumably the fabric of reality itself, must be granular, made of tiny, discrete packets. When we try to apply the quantum rulebook to gravity, to describe the fabric of spacetime as being made of tiny quanta, the mathematics of general relativity completely breaks down. The equations produce nonsensical answers, infinities that cannot be removed. It is as if the smooth, deterministic canvas of the cosmos is fundamentally incompatible with the pixelated, probabilistic rules that govern everything painted upon it. We are left with two perfect yet opposing descriptions of reality, each supreme in its own domain, each refusing to speak the other's language. This mathematical conflict is not a distant academic argument. It becomes terrifyingly real in the most extreme places the universe can create. To see the incompatibility in its raw, destructive form, we must journey to the edge of known physics, to a point of infinite density called a singularity. According to general relativity, when a massive star collapses completely under its own gravity, it does not stop. It crushes itself down past all physical limits, warping spacetime so severely that it pinches off from the rest of the universe, forming a black hole. At the very heart of that black hole, the equations predict a point where all the star's mass is compressed into an infinitely small, infinitely dense pinprick. Spacetime curvature there becomes infinite, gravity becomes infinite. Our familiar laws of physics simply cease to have any meaning. This is the singularity. It is the same type of point that, according to our best cosmological models, existed at the very beginning of everything, at time zero of the Big Bang. A place where the entire universe was once contained in an infinitely hot, infinitely dense state. Now, infinity is not a physical quantity. It is a mathematical warning sign, a scream from the equations that something is profoundly wrong. General relativity is telling us that gravity becomes so strong at these tiny scales that its own description fails catastrophically. This is where we desperately need our quantum rulebook to step in and explain what is truly happening. But when we try to apply quantum mechanics to this extreme gravity, to describe the fabric of spacetime itself as being made of tiny, discrete pieces at the singularity, the mathematics does not just struggle. It explodes. Calculations that work perfectly for every other force produce infinite, nonsensical answers that cannot be corrected. It is a complete dead end. So we are left with a chilling paradox, our best theory of the large-scale cosmos, general relativity, confidently predicts that singularities must exist. Yet our best theory of the small-scale world, quantum mechanics, is utterly incapable of describing them. This means we have no scientific language whatsoever for the very birth of the universe or for the ultimate fate of matter inside a black hole. The singularity is the starkest possible evidence that our two pillars of physics are not just different, they are fundamentally, violently incompatible when pushed to their limits. To understand the origins and ultimate endings of our cosmos, we must find a theory that can speak to both. The singularity is not the only place where our theories wage a silent war. There exists a second, more subtle conflict, one that permeates every single cubic centimeter of seemingly empty space. This is the problem of the vacuum, and it reveals a mathematical mismatch of such staggering proportions it has been called the worst theoretical prediction in the history of science. To understand it, we must look at what quantum mechanics says about nothingness. In the quantum world, a perfect vacuum, a region of space completely devoid of particles, is not empty at all. It is a seething, bubbling foam of activity. Due to the fundamental uncertainty principle, pairs of virtual particles and their antiparticles are constantly flickering into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other. This quantum jitter means that empty space possesses a background energy, a hum of infinite potential known as vacuum energy. When physicists calculate the density of this vacuum energy using the established rules of quantum field theory, they arrive at a number. And that number is catastrophically, unimaginably large. In fact, this predicted vacuum energy density should be so enormous that its gravitational effect, according to Einstein's equations, would cause the very fabric of spacetime to curve upon itself with unbelievable violence. The universe would either have ripped itself apart instantly after the Big Bang or collapsed back in on itself almost immediately. Neither of these things happened. Our universe is billions of years old, and as we now know, its expansion is actually accelerating. This acceleration is driven by something we call dark energy, which acts like a mild, repulsive force woven into the fabric of space itself. Observations from telescopes tell us the density of this dark energy is incredibly small, but not zero. Here lies the disaster. The vacuum energy density predicted by quantum theory and the observed dark energy density measured by astronomers are both attempts to describe the energy of empty space. Yet they disagree not by a little but by a factor of 1 followed by 120 zeros. This is not a rounding error. It is a discrepancy so vast that writing it out would fill multiple lines of text. It means our two foundational theories are off by a number greater than the total number of particles in the observable universe. This vacuum catastrophe is a quiet, persistent scream from our mathematics, telling us that something fundamental in our understanding of quantum fields or gravity or both is profoundly and mysteriously wrong. While singularities represent a violent clash at extreme boundaries, this problem shows the rift exists even in the calm, empty spaces between the stars. Faced with such glaring contradictions, physicists did what they always do. They got to work. In the decades following Einstein, the logical first step seemed clear. Since quantum field theory had so brilliantly tamed the other three forces by describing them as exchanges of particles, why not do the same for gravity? The goal was to quantize gravity, to treat it not as curved geometry, but as a force carried by a hypothetical particle which they named the graviton. This particle would be the quantum of the gravitational field, just as the photon is the quantum of light. The approach was methodical and hopeful. You start with Einstein's equations for general relativity, which describe gravity as the curvature of spacetime. Then you apply the established mathematical machinery of quantum field theory, treating the gravitational field as something that can vibrate and have its own quantum excitations. Early calculations suggested this graviton would be a massless particle with a unique property, a spin of 2, which fit elegantly with gravity's long-range, always attractive nature. For a while, it seemed like a direct path forward, a way to simply add gravity to the Standard Model's triumphant list. But as theorists dug deeper into the mathematics, a terrifying pattern emerged. Every time they tried to calculate what happens when two gravitons interact or scatter off one another, their equations produced not clean, finite answers but infinities. Now, infinities had appeared before in quantum field theory, notably in the development of quantum electrodynamics, which describes how light and matter interact. There, brilliant minds like Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga developed a clever mathematical procedure called renormalization. Think of it as a careful accounting trick. The infinities that popped up in calculations were not signs of real, physical phenomena, but artifacts of the mathematical method. Renormalization provided a systematic way to subtract these infinite quantities in a controlled manner, leaving behind the finite, exquisitely precise numbers that matched experiments perfectly. It was like having a ledger with two columns that both read infinity. By carefully subtracting one infinity from the other, you could reveal the actual finite balance underneath. This technique became a cornerstone of the Standard Model, allowing it to make its legendary predictions. But when physicists applied the same renormalization toolkit to the quantum version of gravity, it failed completely. The infinities that arose were not the manageable kind. They were more numerous, more vicious, and they piled up in a way that no subtraction could ever resolve. Gravity, it turned out, was non-renormalizable. This was not a technical hiccup. It was a fundamental roadblock screaming that gravity was not just another force to be added to the list. Treating spacetime curvature as a quantum field on a fixed background was a profound mistake. The mathematics was telling them, in no uncertain terms, that the very stage upon which the quantum drama plays out cannot be passive. It must be part of the cast. This first major defeat revealed a deep truth. Uniting quantum mechanics and gravity would require not just a new equation, but a completely new kind of thinking. The failure of quantizing gravity directly was a humbling lesson. It forced physicists to confront a radical possibility. Perhaps the problem was not with the math, but with the very picture of reality the math was trying to describe. What if the fundamental ingredients of the universe were not zero-dimensional points, those infinitesimal dots we imagine as electrons and quarks? What if they were something else entirely? This line of questioning gave birth to the first truly comprehensive candidate for a unified theory, a paradigm shift so profound it reimagined the fabric of existence. This is string theory. Its core premise is deceptively simple, yet its implications are universe-shaking. String theory proposes that at the most fundamental level, the building blocks of nature are not point-like particles. Instead, they are unimaginably tiny, one-dimensional filaments of energy, vibrating strings. Think of the strings on a violin or a guitar. A single string, depending on how it is plucked or bowed, can produce a whole spectrum of distinct musical notes, from a deep, resonant hum to a high-pitched chirp. In string theory, each distinct vibration mode of these fundamental strings corresponds to a different particle. One specific vibrational pattern might be an electron. A different, more energetic resonance might be a quark. And crucially, one very special vibration pattern perfectly matches the properties predicted for the graviton, the hypothetical quantum of gravity. In this elegant framework, gravity is not an awkward guest forced into the quantum party. It is a natural, inevitable note in the cosmic symphony, emerging directly from the vibrations of the strings themselves. This was the breathtaking promise. String theory was not merely adding gravity to an existing list. It was proposing a single underlying entity, the string, from which all particles and all forces, including gravity, naturally arise. It offered a mathematically compelling vision of unity, where the zoo of particles in the Standard Model and the force of gravity itself are all just different manifestations of the same basic substance, different chords played on the same tiny instruments. For the first time, a theory had emerged that did not treat gravity as an afterthought, but wove it intrinsically into the quantum description of matter. The mathematical beauty of this idea was, and remains, powerfully seductive. It suggested that the deepest laws of the universe might be governed by a kind of vibrational harmony, a geometry of strings dancing through a higher dimensional reality. But as we would soon discover, this elegant solution came with a price, introducing concepts that would challenge our most basic intuitions about space, time, and the nature of reality itself. String theory's elegance was intoxicating, offering a single answer to the universe's deepest split. But this mathematical harmony came with a startling requirement, one that would redefine our picture of reality itself. For the equations of string theory to work, for the vibrational notes to produce a stable universe with gravity included, they demanded a specific number of dimensions. Not the 4 we experience, space and time, but 10. The theory was telling us our reality is fundamentally 10-dimensional. This was not a suggestion. It was a non-negotiable condition for mathematical consistency. Without these extra dimensions, the equations descended into chaos, producing the same infinities and inconsistencies that plagued the old quantum gravity attempts. So the question became immediate and profound. If there are 10 dimensions, where are the other 6? Why do we only perceive the familiar 3 of space and 1 of time? The answer proposed by string theorists is one of the most fascinating ideas in modern physics, a concept called compactification. Imagine a long, thin garden hose stretching far into the distance. From a great distance, it looks like a simple one-dimensional line. But if you walk right up to it, you see it has a second dimension, a circular cross-section, curled tightly around its length. An ant living on the surface of that hose would experience 2 very different realities. Moving along the hose's length, it could travel a long, long way. But moving around its circumference, it would circle back to its starting point almost instantly. To a human observer far away, that circular dimension is invisible, hidden by its tiny, curled-up scale. String theory suggests our universe is like that, but on a far more complex scale. The 3 large spatial dimensions we know, length, width, and height, are like the long axis of the hose extended across the cosmos. The 6 extra dimensions required by string theory are theorized to be like that circular cross-section, but curled up into incredibly intricate, tiny shapes at every single point in space. These shapes are not random. They are specific 6-dimensional geometric forms known as Calabi-Yau manifolds, named after the mathematicians who studied them. Each is a complex, twisted landscape of folds and holes, existing at a scale a billion times smaller than an atomic nucleus. This is why we do not notice them. They are simply too small for any particle or instrument we have to probe. But according to the theory, the precise geometry of these hidden, compactified dimensions is not just decoration. It is everything. The way a string vibrates is determined by the shape of the space it moves through. Just as air flowing through different shaped wind instruments produces different musical notes, a fundamental string vibrating through the specific folded geometry of a Calabi-Yau manifold determines what kind of particle it becomes. The number of holes and twists in this hidden landscape would dictate the properties of the particles we see, like their mass and charge. In one stroke, this shifted the entire search for a unified theory. The problem was no longer just about finding the right equations for particles and forces in 4 dimensions. It became a problem of geometry in 10. The quest for a theory of everything transformed into a search for the one true shape, the single, correct six-dimensional geometry hidden at the heart of every point in our reality, whose vibrational patterns would exactly reproduce our universe with all its particles and forces. It was a breathtaking, if bewildering, new vision of cosmic architecture, but this elegant vision of hidden dimensions came with a devastating trade-off. For all its mathematical beauty, string theory faced a growing and fundamental criticism, one that strikes at the very heart of the scientific method. Where were the predictions? A good scientific theory must do more than explain what we already see. It must make bold, testable forecasts about what we have not yet observed, allowing experiments to prove it right or wrong. Yet decades of intense work on string theory seem to produce no clear, unique prediction for an experiment we could actually perform. The reason for this silence lies in a concept that transformed a promise of unity into a landscape of staggering possibility. This is the string theory landscape. Recall that the properties of our universe, from the mass of an electron to the strength of gravity, are determined by the shape of those six hidden, curled-up dimensions. The mathematics of string theory does not point to a single, perfect shape for these Calabi-Yau manifolds. Instead, it allows for an absolutely mind-numbing number of them. Current estimates suggest there could be 10 to the power of 500 distinct, stable configurations. That is a 1 followed by 500 zeros, a number so vastly larger than the total number of particles in our observable universe that it defies any meaningful analogy. Each of these possible shapes represents a different vacuum state, a different stable configuration for the fabric of reality, and each vacuum state corresponds to a different possible universe with its own unique set of physical laws and constants. In one such universe, the electromagnetic force might be stronger, preventing atoms from forming. In another, the cosmological constant could be immense, causing instant cosmic collapse. Our universe, with its specific, life-permitting numbers, would be just one tiny bubble in this incomprehensibly vast cosmic landscape of possibilities. This presents a profound philosophical and scientific dilemma. If the theory allows for 10 to the 500 different versions of reality, how can it uniquely predict ours? Instead of providing a single, elegant answer for why the laws of physics are what they are, string theory seemed to be offering a near infinity of answers. Our existence here would not be dictated by a fundamental equation, but would be the result of a cosmic accident, a random selection from a nearly endless menu. To many critics, this moved the theory from the realm of testable science into the domain of metaphysics. If we can always find some configuration in the landscape that matches any new observation, then the theory cannot be falsified. It risks becoming a narrative of post hoc explanation rather than an engine of genuine prediction. The landscape problem forced a painful question. Had the long search for a single, unifying theory led us instead to a multiverse of disconnected possibilities, where the dream of a unique theory of everything might be forever out of reach? Yet the landscape was not the only path forward. While string theory dominated the conversation with its extra dimensions and vibrating strings, a radically different idea was taking shape in the shadows. This rival approach refused to start from the quantum world and force gravity to fit. Instead, it began with Einstein's sacred principle that gravity is geometry. Its goal was not to quantize a force, but to quantize spacetime itself. This is loop quantum gravity, and it asks a question string theory does not. What if the smooth, continuous fabric of general relativity is an illusion? A kind of cosmic mirage that vanishes when we look closely enough. Loop quantum gravity proposes that at the tiniest imaginable scale, the Planck-scale, which is about 10 to the minus 35 meters, spacetime is not smooth. It is not a fabric, it is a tapestry woven from individual threads. Picture a mesh, a network of interconnected loops, like an unimaginably fine chainmail. Each loop represents a tiny, indivisible quantum of area. The intersections where these loops join are the quanta of volume. This structure is called a spin network, and it is the fundamental bedrock of reality in this theory. Space itself is not a background stage. It is this evolving, dynamic web of relationships. In loop quantum gravity, there is no such thing as an infinitely small point. You cannot divide a volume or an area forever. There is a smallest possible unit, just as a digital photograph is made of individual pixels. This solves the singularity problem in a breathtakingly direct way. The core of a black hole is not a point of infinite density, because the quantized fabric of space cannot be compressed beyond its smallest possible volume. The collapse simply stops. Similarly, the Big Bang was not a true singularity from nothing. It may have been a big bounce, a moment where a previous universe contracted to a minimum size before rebounding into our own expansion. The theory provides a natural limit, a granularity that prevents the mathematical infinities that destroy other approaches. It is a vision that honors Einstein's geometric insight, while insisting that even geometry must obey the quantum rule that everything comes in discrete packets. Here, gravity is not mediated by a particle moving through space. Gravity is the geometry of space, and that geometry is quantum. Loop quantum gravity offers a radical and compelling solution to the most violent paradoxes in physics. Its greatest achievement is its direct, almost surgical resolution of the singularity. Because space itself is woven from indivisible quanta, there is a hard limit to how tightly it can be squeezed. In the heart of a black hole, matter does not collapse into an infinitely dense point. Instead, it compresses down to a finite, maximum possible density, at which point the intense quantum geometry creates a repulsive force. This repulsion could potentially halt the collapse entirely or even reverse it, turning the black hole's core into a gateway to another region of spacetime. Similarly, this granularity rewrites our cosmic origin story. The Big Bang was not a moment of infinite density emerging from nothing. In the loop quantum gravity picture, it was likely a big bounce. A previous phase of the universe contracted down to this same maximum density, and then quantum gravitational effects caused it to rebound, exploding outward into the expansion we observe today. This replaces a singular beginning with a transformational transition, offering a glimpse beyond the veil of time zero. This resolution is not just a mathematical trick. It stems from the theory's core philosophical strength, a principle called background independence. Unlike almost every other framework, loop quantum gravity does not require a pre-existing stage of spacetime for its quantum events to play out on. The spin network is not embedded in space, it is space. The relationships between its loops define distance and geometry dynamically from the ground up. In this view, gravity is not a force acting on a stage. It is the quantum dynamics of the stage itself, finally brought under the quantum rulebook. This elegant, self-contained nature is its most profound conceptual appeal. Yet for all its conceptual beauty, the theory faces monumental challenges on the path to becoming a complete description of reality. The mathematics of weaving a universe from spin networks is extraordinarily complex, making concrete calculations of real-world phenomena incredibly difficult. Furthermore, a major test for any theory of quantum gravity is whether it can smoothly recover the familiar, classical world of general relativity on the large scales where we know Einstein's equations work perfectly. Demonstrating that a universe built from discrete loops naturally looks like a smooth, continuous fabric across stars and galaxies is an ongoing and formidable struggle. Perhaps the most significant hurdle is unification itself. While loop quantum gravity provides a compelling quantum picture of spacetime geometry, it has not yet naturally incorporated the other forces of nature, the particles and interactions of the standard model, into its woven fabric. String theory began with unity as its primary goal, weaving all forces from the vibrations of strings. Loop quantum gravity began by rigorously quantizing gravity itself, with the hope that matter could be added later. To this day, successfully weaving the full particle zoo into the spin network remains an unfinished and critical piece of the puzzle. So we are left with two magnificent yet incomplete visions. One paints reality as vibrating strings in hidden dimensions, promising unity at the cost of a vast, untestable landscape. The other depicts reality as a woven quantum geometry, solving singularities with pure geometry, but still searching for the thread that ties all forces together. While string theory and loop quantum gravity dominate the debate, a quieter third path has been steadily gaining ground, one that asks a deceptively simple question. What if we have been giving up on the original idea too soon? This approach does not require extra dimensions or a woven spacetime. Instead, it revisits the very problem that first defeated physicists, the issue of renormalization, and suggests a subtle, ingenious way through. It is called asymptotic safety in quantum gravity, and its core idea is a beautiful piece of mathematical insight about how nature might behave at its most extreme limits. To understand it, we must first revisit that critical moment when the old quantum gravity effort failed. Remember, the attempt to treat gravity like the other forces led to uncontrollable infinities. The mathematical procedure of renormalization, which worked perfectly for electromagnetism and the nuclear forces, could not tame gravity's equations. The theory was deemed non-renormalizable, meaning its infinities were incurable, and that seemed to be the end of the story. But asymptotic safety proposes a different ending. It suggests that gravity might become renormalizable after all, not by adding new ingredients, but by following its behavior across every possible energy scale with exquisite care. Imagine you are observing a river. From one vantage point, it looks chaotic, full of dangerous whirlpools and unpredictable currents. This is like viewing gravity at the high energies of the Big Bang or a black hole singularity, where our calculations break down. But if you could see the entire river's course from its source in the mountains all the way to the calm delta where it meets the sea, you might notice a pattern. Perhaps every turbulent stretch eventually flows into a deep, stable pool before continuing on. In the language of physics, this journey across scales is called the renormalization group flow. It is a mathematical map that shows how the strength of a force, or a coupling constant, changes as you probe higher and higher energies. For a theory to be consistent and finite at all energies, this flow must lead to a special, stable point. For the other forces, this point is a trivial fixed point, like a ball resting at the very bottom of a valley. Any small push representing a change in energy, and the ball rolls back to the bottom, keeping the theory's behavior predictable and finite. This is why renormalization worked for them. Gravity's flow, however, seemed to lead off a cliff into infinity. Asymptotic safety proposes a stunning alternative. What if gravity's flow does not lead off a cliff, but instead to a different kind of stable point, a non-trivial fixed point? Picture not a valley bottom, but the precise apex of a steep, smooth hill. It is an unstable equilibrium. If a ball is placed exactly at the top, it will stay there, but the slightest nudge in any direction will send it rolling away. In this metaphor, the ball's position represents the strength of gravity's interactions. The asymptotic safety hypothesis is that at incredibly high energies, near the Planck-scale, the flow of gravity's parameters reaches just such a precarious peak. If the universe's initial conditions placed it exactly on that point, then, as energies decrease, the flow would trace a specific, unique path down from the peak, like a single, predetermined watercourse down the mountainside. This path is called an ultraviolet complete trajectory. Following this exact path ensures that the theory remains well-behaved and produces finite answers at all energies. from the violent quantum furnace of the early universe down to the gentle orbital dances we see today. In this picture, there is no need for strings or loops. Gravity becomes a perfectly consistent quantum field theory in the familiar 4 dimensions, its former infinities tamed not by subtraction, but by the elegant geometry of its own mathematical journey across the scales of reality. The appeal is profound. It is a minimalist dream modifying Einstein's original framework as little as possible while still achieving quantum consistency. The challenge, of course, is proving that this beautiful fixed point actually exists in the complex mathematics of quantum gravity. Researchers use sophisticated approximations to search for it, and recent decades have provided encouraging hints that such a point may be there, waiting to be found with full precision. It is a path less traveled, but one that holds the promise of unity through subtlety, suggesting that the key to the universe's deepest rift might lie not in reinventing reality, but in understanding the perfect, stable shape of gravity's own hidden journey. There is another path, one that builds reality not from strings or loops, but from a cosmic game of chance. This is the approach of causal dynamical triangulations, and it asks a disarmingly simple question. What if the smooth, 4-dimensional universe we live in is not a fundamental given, but a statistical average, a pattern that emerges from pure randomness when you apply just one crucial rule? To find out, this theory turns to the power of computation, constructing spacetime from the ground up, one tiny piece at a time. The building blocks are not mysterious strings or abstract networks, but the simplest geometric shapes possible in any dimension, known as simplices. In 2 dimensions, a simplex is a triangle. In 3, it is a tetrahedron. In the 4 dimensions of spacetime, it is a 4-dimensional analog called a pentachoron. Think of these as the cosmic Lego bricks of reality. The theory's recipe is straightforward, yet profound. You take an enormous number of these 4-dimensional blocks, and you start gluing their faces together, completely at random. You allow every possible connection, every bizarre, crumpled configuration you can think of, creating a vast and chaotic quantum soup of possible universes. This is where the magic word in its name comes in, causal. You do not allow just any random glue job. You impose one non-negotiable physical rule from our own universe, the law of causality. Cause must always come before effect. In the geometry of these blocks, this translates to a strict order in time. You cannot glue blocks together in a way that creates closed time like loops or situations where an effect could theoretically influence its own cause. This single rule, woven into the randomness, acts as a cosmic filter. With causality enforced, you then let a supercomputer perform a monumental statistical sum. It calculates the probability of every single possible glued-together configuration, every possible history of this block universe, and it adds them all together, just as quantum mechanics tells us to do for all possible paths a particle can take. What emerges from these digital experiments is nothing short of astonishing. When the simulation runs, that initial soup of chaotic, random blocks does not remain a disordered mess. Without any further instructions, it spontaneously organizes itself. The multitude of random paths cancel each other out, except for one overwhelmingly probable configuration. And that configuration is a smooth, extended, classical 4-dimensional spacetime, remarkably like our own. It is as if you told a room full of people to move randomly, but with the one rule that they cannot bump into each other. From that simple constraint, orderly lanes of traffic would naturally form. Causal dynamical triangulations demonstrates that the familiar geometry of our universe, with its clear distinction between space and time and its predictable large-scale behavior, could be a natural, emergent phenomenon. It is the average result of a trillion quantum possibilities, all obeying the fundamental principle that cause precedes effect. This offers a powerful and tangible vision for how the smooth canvas of Einstein's relativity could crystallize out of the seething, discrete quantum world, not by design, but by the relentless statistics of simplicity and order. The universe built from random blocks reveals a deep truth: that order can emerge from chaos under the right rule. But there is an even more radical vision, one that strips reality down to its most essential, minimalist ingredients. This is causal set theory, and it proposes that the fundamental structure of our cosmos is not a smooth fabric, not a woven network, not even a collection of geometric blocks. It is something far simpler, a vast, sparse collection of discrete points, like a cosmic dust scattered through nothingness. These points represent the most basic events, the ultimate atoms of spacetime. In this theory, nothing else is fundamental, not space, not time, not even geometry. There is only this set of events and one single, crucial type of connection between them: the relation of cause and effect. One point is connected to another if, in the most direct physical sense, the first event can influence the second. A photon is emitted here, point A, and later absorbed there, point B. That creates a causal link. This web of pure causality, this vast collection of dots connected by arrows of influence, is the entire foundation. Everything we think of as the universe, the smooth flow of time, the three-dimensional expanse of space, the curvature of gravity described by Einstein, all of it is secondary. These are approximate, emergent concepts that arise from the pattern of this underlying causal network when you look at it from a distance. Think of a sheet of newspaper. Up close, you see it is not a smooth, gray surface at all. It is a precise arrangement of tiny, discrete black ink dots on white paper. The picture of a face or a landscape that you see from a few feet away is not fundamentally in the dots. It emerges from their specific pattern and density. In causal set theory, the smooth, four-dimensional spacetime of our experience is exactly that kind of large-scale image. The dots are the fundamental events, and the causal links are their arrangement. The geometry of the universe, the very distance between stars, is not a primary quality. It is a consequence of how many causal links lie between the events representing those stars. This idea carries a profound philosophical elegance. It takes the most sacred principle from Einstein's relativity, the unbreakable speed limit of light and the causal structure it creates, and elevates it to the status of the only reality. Matter and energy do not move through space and time. They are manifestations of the pattern of this causal set. The theory is breathtaking in its austerity, building everything from the barest relational skeleton of cause and effect. Yet this minimalist approach faces its own immense challenge: the problem of recovery. How exactly does the rich, continuous, geometric world of planets and galaxies, so perfectly described by Einstein's smooth equations, emerge from this sparse collection of points and links? How do you get a three-dimensional space from a structure that does not start with dimensions at all? This is the active frontier of the theory, to show that if you take a random, growing causal set and apply the right statistical and geometric reasoning, the familiar picture of a four-dimensional spacetime universe is the most likely, the most natural thing to appear. It is a gamble on simplicity, a bet that the universe at its heart is nothing more than a story of connected events, and that all the stagecraft of space and time is merely the way that story feels when we are living inside it. But the most startling vision of all might be one that suggests our three-dimensional reality is an illusion, a cosmic projection. This is the holographic principle, a radical reformulation of reality that emerged from the fiery intersection of black hole physics and string theory. Its central idea is as simple as it is profound, that all the information needed to describe everything within a volume of space, every star, every atom, every fleeting thought, can be perfectly encoded on a surface that surrounds it, a boundary with one less dimension. Imagine the universe as a three-dimensional movie, complete with depth and movement. The holographic principle suggests that the entire film, every character and every scene, is actually stored on a flat, two-dimensional screen encircling it. The world we experience is not the primary reality, it is a projection, a hologram. This is not science fiction, but a serious mathematical framework born from a deep puzzle about black holes. When matter falls into a black hole, it seems to vanish, taking all information about itself with it. This creates a paradox because quantum mechanics insists information can never be truly destroyed. In the 1970s, physicist Jacob Bekenstein made a crucial discovery. He found that the maximum amount of information, or entropy, a black hole can contain is not proportional to its volume, as you might expect, but to the area of its event horizon, the two-dimensional surface that marks its point of no return. It was as if all the complexity of the black hole's interior was somehow painted onto its surface. This area law was the first hint that the true degrees of freedom of a space might live on its boundary, not within it. Decades later, string theory provided a breathtakingly concrete example of this principle, a mathematical gem known as the anti-de Sitter conformal field theory correspondence, or AD-SCFT. It describes a precise one-to-one duality between two completely different worlds. On one side is a universe with gravity, a special, negatively curved space called anti-de Sitter space. On the other side is a quantum field theory that lives on the infinitely distant boundary of that space, a flat world without gravity at all. The miracle of this correspondence is that these two theories, one with gravity in a bulk volume and one without gravity on its boundary, are mathematically and physically equivalent. They are two perfectly interchangeable descriptions of the same underlying reality. A complex event involving black holes and warped spacetime in the gravitational bulk can be translated, without any loss of information, into a tremendously complicated but ordinary quantum interaction on the boundary. The gravity-filled world is a holographic projection of the information processing happening on its lower dimensional edge. While our universe is not precisely an anti-de Sitter space, the power of this example is undeniable. It shows that a theory of quantum gravity can be completely equivalent to a quantum theory without gravity in fewer dimensions. The holographic principle forces us to ask a staggering question. Could our own rich, four-dimensional spacetime, with all its galaxies and forces, be nothing more than a magnificent hologram, projected from a vast, complex quantum system living on a distant, cosmic horizon we cannot see? This holographic view of reality carries staggering implications, shaking our most basic assumptions about the universe. If true, it means that the three-dimensional world we move through, with all its solidity and depth, is not the fundamental layer of existence. It is an emergent phenomenon, a grand illusion projected from a vast, flat cosmic code. This radically redefines a core concept in physics known as locality. In our everyday experience, objects interact because they are close together in space. A magnet pulls on a paperclip because they occupy neighboring locations. Locality is the rule that things must be in contact or connected by a field to influence one another. But in a holographic universe, this is a surface-level truth. The real interactions, the fundamental computations that generate the illusion of a magnet and a paperclip, are happening on a distant, two-dimensional boundary. What looks to us like a local event in three-dimensional space is the result of non-local information processing on a surface we can never see. The objects in our world are not separate entities in empty space. They are entangled projections of a single, unified source code written on the edge of reality. Beyond this philosophical earthquake, the holographic principle provides physicists with something incredibly rare in the search for quantum gravity, a powerful, practical tool. Through frameworks like the AD-SCFT correspondence, it creates a mathematical dictionary. This dictionary allows you to translate a problem that is impossibly difficult in one description into a problem that is much easier to solve in the other. One of the most fruitful applications has been in studying exotic states of matter known as strongly interacting quantum systems. Imagine trying to understand the behavior of a substance where the particles are so fiercely entangled that they act as a single, chaotic collective. A perfect example is the quark-gluon plasma, a state of matter that existed a microsecond after the Big Bang and can be recreated momentarily in particle colliders. Calculating its properties using standard quantum field theory is a computational nightmare, but through the holographic dictionary, this fiery, complex quantum soup can be translated into the physics of a black hole in a higher dimensional gravitational space. The temperature and viscosity of the plasma become questions about the temperature and dynamics of the black hole's event horizon. Suddenly, an intractable quantum problem becomes a tractable problem in gravitational geometry. Researchers can use the well-understood equations of general relativity to make predictions about the quark-gluon plasma, and those predictions have been confirmed by experiments. This is not just a neat trick. It is a profound validation that this holographic duality captures something deeply true about the fabric of reality, even while a complete, standalone theory of quantum gravity for our own universe remains just out of reach. The principle gives us a working bridge between the quantum and gravitational worlds, allowing us to explore the territory of their union long before we fully map it. Yet these breathtaking ideas, from vibrating strings to holographic projections, share a common and profound challenge. They exist in an experimental desert. For all their mathematical beauty and conceptual power, we possess almost no direct evidence to confirm or refute them. The central reason is a simple, brutal number, the Planck energy. This is the energy scale at which quantum gravitational effects are expected to become dominant, where the fabric of spacetime itself should reveal its true, grainy nature. To reach it in a laboratory, we would need to build a particle collider roughly the size of our entire galaxy. It is a barrier not of engineering, but of fundamental physics and cosmic scale, placing the most direct test of these theories forever beyond our physical grasp. This does not mean physicists have given up. Instead, they have become cosmic detectives, searching for subtle, indirect signatures that these theories might have left etched into the universe. One promising frontier is the cosmic microwave background, the faint afterglow of the Big Bang. Theorists scrutinize its minute temperature fluctuations, looking for imprints that could only have been made in the universe's first fleeting instance when quantum gravity ruled. Perhaps a specific pattern in this ancient light could reveal the vibrations of strings or the granular structure of spacetime from the dawn of time. Another window opened with the first detection of gravitational waves, ripples in spacetime from colliding black holes and neutron stars. As our observatories grow more sensitive, they may catch whispers of exotic phenomena predicted by these theories. Could we detect a faint echo in the gravitational wave signal, a hint of a quantum structure at a black hole's event horizon, or find a deviation from Einstein's predictions at extreme energies? Scientists also look upward to the cosmos itself for natural particle accelerators, ultra-high-energy cosmic rays, atomic nuclei hurtling through space with energies millions of times greater than anything we can produce on Earth, occasionally strike our atmosphere. By studying the elaborate particle showers they create, researchers hunt for anomalies that might betray a breakdown of standard physics at energies closer to the Planck scale. Meanwhile, in quiet laboratories, a different kind of hunt is underway. Tabletop experiments use exquisitely precise instruments, like interferometers or superconducting devices, to probe whether spacetime is truly smooth or has a minute, granular texture. They look for a subtle blurring or noise that might emerge if light or matter is traveling across a reality built from discrete pixels, much like a digital image loses clarity when you zoom in too far. The search is a testament to human ingenuity, turning the entire universe into a laboratory and every ancient photon into a potential messenger. While we may never recreate the Big Bang in a machine, its echoes and its ongoing evolution may still carry the faint, decipherable signature of a deeper, unified truth. This experimental desert makes the cosmos itself our most powerful instrument, and within it, black holes stand as the ultimate natural laboratories for quantum gravity. These are not just cosmic vacuums, they are the only places in the universe where the war between our two foundational theories plays out in real time with observable consequences. The central drama is the black hole information paradox, a puzzle so deep it threatens the logical consistency of all physics. According to Stephen Hawking's revolutionary work, black holes are not truly black. Quantum effects near their event horizons cause them to slowly leak radiation and evaporate over astronomical timescales. This Hawking radiation, however, presents a catastrophic problem. The radiation appears to be completely random, carrying no information about the intricate details of the matter that fell in. When the black hole finally evaporates completely, all that unique information about stars, planets, or books seems to be permanently erased from the universe. This violates a sacred principle of quantum mechanics called unitarity, which states that information can never be truly lost, only scrambled and transformed. It is the ultimate conflict, quantum mechanics demanding information preservation, while the semi-classical calculation of Hawking radiation suggests its destruction. Any viable theory of quantum gravity must resolve this paradox. It must tell us what happens to information not as an abstract concept, but as a physical process. Does it slowly leak out encoded in the Hawking radiation? Is it preserved on the remnant surface of a tiny, dense leftover? Or is it stored on the event horizon itself, as the holographic principle suggests? The answer will rewrite our understanding of reality. This is no longer pure theory. For the first time in history, we have tools that can peer toward the edge of these cosmic laboratories. The Event Horizon Telescope, a planet-sized array of radio dishes, has given us our first ghostly images of the shadow cast by supermassive black holes. While these images currently match the predictions of Einstein's classical theory, future observations with more telescopes and higher frequencies could reveal subtle deviations. Does the shadow's shape or the ring of light around it show signs of a quantum fuzziness, a microstructure at the horizon that smooth general relativity cannot predict? Even more promising are gravitational wave observatories. When two black holes spiral together and merge, they shake the fabric of spacetime, sending ripples across the cosmos. The precise shape of these gravitational wave signals is a detailed fingerprint of the merger. As our detectors become more sensitive, they might catch echoes in the signal, a faint ring-down after the main collision that could hint at exotic physics just outside the event horizon. Perhaps the waves will reveal signs of a quantum structure, a hard surface or a fuzzball of strings, rather than the perfectly smooth void of classical theory. Every black hole merger we listen to is not just a cosmic catastrophe, it is a message. Within the faint chirp of colliding space-time, there might be hidden clues about the true, unified nature of gravity, written in a language we are only just beginning to understand. The silent whispers from black holes may be our most direct clues, but to understand the universe's very first moment, we must look to the grandest canvas of all, the cosmos itself. Cosmology, the study of the universe's origin and evolution, provides the ultimate historical record for testing theories of quantum gravity. Its central story, the Big Bang, presents the most extreme scenario imaginable. Rewind the expansion we see today, and everything we know, every galaxy and atom, converges back to an initial state of unimaginable density and temperature. According to classical general relativity, this starting point is a singularity, a moment where the equations break down and our understanding ends. But this is precisely where quantum gravity must take center stage. The first fleeting instants of the universe were a realm where the energy was so high and scales so small that the quantum nature of spacetime itself would have dictated the rules. The Big Bang is not just an event in our past, it is the primary crime scene for the mystery of quantum gravity. Our task is to find the evidence it left behind. Different theories paint wildly different pictures of this primordial epoch. Loop quantum gravity, with its granular spacetime, suggests there was no true beginning from nothing. Instead, our universe may have been born from a big bounce, a prior cosmic phase that contracted to a minimum size before quantum repulsion triggered the expansion we see today. This transforms a singular origin into a cosmic transition, a turning of the page in an eternal story. String theory, on the other hand, offers various cosmological models where the dynamics of those extra, curled-up dimensions or networks of colliding brains, higher dimensional objects, could have sparked our universe's birth. In these visions, the Big Bang might have been a collision, a symmetry breaking, or a phase change in a higher dimensional reality. The critical question for all these ideas is the same: did they leave a detectable fingerprint on the universe we inhabit today? The answer lies in the oldest light we can see, the cosmic microwave background. This faint, uniform glow is the cooled remnant of the hot, dense plasma that filled the young universe. It is a snapshot from when the cosmos was just 380,000 years old. Imprinted upon this glow are tiny, 1 part in 100,000, variations in temperature. These ripples are the seeds of all future structure, the galaxies and clusters we see today. They were created by quantum fluctuations in the even more primordial universe, stretched to cosmic size by a brief, explosive period of hyper-expansion called inflation. This is where the search gets incredibly precise. The specific pattern of these ripples, their distribution across different angular scales on the sky, is a direct record of the physics operating in that first trillionth of a second. Theories of quantum gravity make subtle, specific predictions for how they might alter this pattern. Could the granular structure of spacetime in loop quantum gravity have left a specific signature in the way the largest scales in the universe are correlated? Might the vibrational modes of strings or the dynamics of extra dimensions have produced a characteristic twist in the polarization of this ancient light, a specific swirl pattern that standard inflation does not predict? By mapping the cosmic microwave background with exquisite detail, missions like the Planck satellite and future observatories are essentially conducting archaeology on the universe's first moments. They are not looking for the blast itself, but for the subtle cracks in the foundation, the tiny imperfections that only a quantum theory of gravity could have created. Furthermore, the large-scale structure of the universe, the vast cosmic web of galaxies and dark matter, also holds clues. The way galaxies cluster and flow on the largest scales carries echoes of those initial conditions. If quantum gravity altered the primordial seed fluctuations in a specific way, that alteration should be woven into the distribution of matter we see billions of years later. Cosmology offers a beautiful, if indirect, path forward. We may never build a machine that recreates the Big Bang, but we have a time machine built into the sky itself. By reading the faint patterns in the light from the edge of time, we might finally decipher the handwriting of quantum gravity, written in the first moment of everything. The search for a single, unified theory of reality has led us to a breathtaking yet deeply unsettling possibility. What if our universe is not alone? What if it is just one bubble in an infinite, frothing sea of other universes, each with its own unique laws of physics? This is the Multiverse Hypothesis, and it has emerged not from science fiction, but directly from the mathematical heart of our best attempts to unite quantum mechanics and gravity. Yet it sparks a fierce debate, forcing us to ask whether this is the ultimate prediction of our theories, or a philosophical dead end that risks ending science itself. The path to the multiverse begins with two powerful ideas we have already explored. The first is string theory's landscape. Recall that the theory allows for perhaps 10 to the 500 different stable configurations for its 6 hidden dimensions. Each configuration corresponds to a different vacuum state, a different set of physical constants and laws. In this view, the multiverse is a vast, static array of every possible universe allowed by the equations, and our cosmos is simply one that happens to allow for stars, planets, and life. We are here not because the laws are uniquely designed, but because we can only exist in a universe that permits us, a concept known as the Anthropic Principle. The second path comes from cosmology, from a refinement of the inflationary model of the Big Bang. This is the theory of eternal inflation. Imagine the energy field that drove the universe's explosive early expansion. Quantum fluctuations could cause this field to drop to a lower energy state in a localized region, like a bubble forming in boiling water. That bubble stops inflating internally and becomes a stable, expanding universe like our own. But outside that bubble, the high-energy inflationary field continues to rage, expanding even faster. In that eternally inflating background, an endless number of other bubbles are constantly nucleating, each becoming a separate universe with potentially different properties, because the way the energy field settles can vary. In this picture, the multiverse is not a static catalog, but a ceaselessly breeding fractal foam of cosmic domains. Together, these ideas from fundamental physics and cosmology converge on a similar, staggering conclusion. If our best mathematical descriptions of quantum gravity and cosmic origins are correct, then a multiverse may not be a speculative add-on. It may be an inevitable consequence. This presents a profound philosophical dilemma. On one hand, it could be seen as the ultimate triumph of scientific extrapolation. We follow the equations wherever they lead, even if they lead to a reality far grander and stranger than we ever imagined. The multiverse, in this view, is a genuine, if indirect, prediction of string theory and inflationary cosmology. It offers an explanation for the seemingly fine-tuned constants of our universe, like the strength of gravity or the cosmological constant. They are not fine-tuned. Every possible value occurs somewhere in the multiverse, and we simply find ourselves in a bubble where the numbers are right for us. On the other hand, critics argue this begins to look less like a prediction and more like a retreat. The original goal was a theory of everything, a single, elegant set of laws that uniquely predicts our one universe. The multiverse hypothesis seems to abandon that dream. If every possible set of laws exists somewhere, then our particular laws require no deeper explanation. The quest for a unique, fundamental reason why things are the way they are becomes meaningless. Worse, it raises a severe challenge to the scientific method itself. Science relies on testability and falsifiability. How can we possibly test for the existence of other universes, forever disconnected from our own by the infinite expanse of eternally inflating space or by different dimensional geometries? If no observation can ever confirm or deny the multiverse, does it cross the line from scientific theory into metaphysics? This debate cuts to the core of what science is and what it can hope to achieve. Proponents of the multiverse idea suggest there might be indirect, subtle tests. Perhaps a collision between our bubble universe and another in the distant past left a peculiar imprint on the cosmic microwave background, a kind of cosmic bruise. Maybe the specific distribution of vacuum energies we observe statistically favors a multiverse scenario over a single, lonely universe. Skeptics counter that such evidence would always be circumstantial and open to other interpretations. The fear is that by invoking a near infinity of unseen worlds to explain the one we see, we might be constructing an unfalsifiable story, a castle in the air built from beautiful mathematics but resting on no empirical foundation. The multiverse stands as the ultimate mirror held up to our search for unity. It shows us where the relentless pursuit of quantum gravity can lead, into realms of staggering scale and existential ambiguity. Whether it is the final, humbling answer or a sign that we have lost our way, is perhaps the most defining question for the next century of physics. It forces us to confront not just the fabric of spacetime, but the very boundaries of scientific explanation itself. This grand intellectual quest, however, is not fought in a vacuum of pure ideas. It unfolds within a very human world of institutions, careers, and fierce debate. For decades, the search for a theory of quantum gravity has been shaped by immense sociological forces, by funding priorities and academic battlegrounds that have profoundly influenced which paths are explored and which voices are heard. The two leading candidates, string theory and loop quantum gravity, have often existed not just as scientific frameworks, but as competing cultures, each with its own conferences, journals, and powerful advocates. String theory, with its elegant promise of ultimate unity, captured the imagination of a generation and, crucially, a dominant share of resources and prestigious positions within theoretical physics departments. This created a powerful gravitational pull of its own, drawing brilliant young minds toward the most active and well-supported area. The result was a kind of intellectual monoculture in many leading centers, where pursuing the landscape of string theory was seen as the mainstream, respectable path to a career. Conversely, approaches like loop quantum gravity, causal set theory, or asymptotic safety were often relegated to the periphery, pursued by smaller, more scattered groups fighting for recognition and funding. This dynamic raises difficult questions about how scientific consensus forms when direct experimental guidance is absent for generations. Without data to decisively settle arguments, progress can become influenced by aesthetic judgments, mathematical trends, and the persuasive power of key individuals. Critics have pointed to risks of groupthink, where challenging the dominant paradigm becomes a professional hazard, especially for researchers early in their careers who need positions and publications. The pressure to produce results within an established framework can discourage the kind of radical, unconventional thinking that might be necessary to finally crack the problem. Imagine a young physicist today captivated by a completely novel approach to quantum gravity that does not fit within the existing camps. To pursue it, they must convince senior researchers, secure grant money, and publish in major journals, all within a system that naturally rewards work that builds upon, rather than overturns, the invested knowledge of decades. The stakes for their personal future are incredibly high, which can subtly steer curiosity toward safer, more incremental questions. This human dimension adds a layer of profound complexity to the scientific challenge. The quest to understand the fundamental architecture of the universe is also a story about how we organize our own collective intelligence, how we allocate limited resources in the face of immense uncertainty, and how we maintain the courage for genuine exploration when the destination is unknown and the map is blank. The history of this field is a testament to extraordinary patience and dedication, but also a cautionary tale about the invisible frameworks we build around our search for truth. Faced with this experimental desert, a quiet revolution has been taking shape. A new generation of physicists is refusing to wait for a galaxy-sized collider or a perfect mathematical proof. Instead, they are asking a pragmatic and urgent question. If our theories are truly descriptions of reality, they must leave some mark, however faint, on the universe we can actually measure. This shift in mindset has given birth to a vital new field, quantum gravity phenomenology. Its mission is disarmingly direct, to bridge the vast chasm between abstract theory and tangible observation. Phenomenologists take the bold mathematical structures of string theory, loop quantum gravity, and other frameworks, and they work backwards, They meticulously calculate what subtle, observational signatures these theories would imprint on the cosmos if they were true. They are not looking for a direct detection of a graviton or a string. They are searching for the inevitable side effects, the cosmic breadcrumbs these deeper structures would leave behind. Their work transforms philosophical speculation into a checklist of potential discoveries, turning the entire observable universe into a forensic lab for the most fundamental physics. One of the most promising hunting grounds involves the very fabric of spacetime and how light travels through it. Many quantum gravity models suggest that spacetime might have a minute, granular structure at the Planck scale, like a digital image viewed under extreme magnification. This pixelation, theorists propose, could affect light in a specific way. Photons of different energies traveling across billions of light-years from cataclysmic events like gamma-ray bursts might experience this granularity slightly differently. A high-energy gamma-ray photon and a lower-energy radio wave, both emitted from the same explosive event at the same moment, might not arrive at our telescopes at exactly the same time. The subtle difference in their arrival times, a phenomenon called a modified dispersion relation, could be the telltale sign that light is bumping against the discrete texture of reality itself. While the effect would be incredibly small, buried in noisy data, observatories like the Fermi Gamma Ray Space Telescope and vast arrays of radio telescopes are now sifting through signals from the most distant and violent events in the universe, searching for this ghostly delay. Another critical frontier is the ancient light of the cosmic microwave background. Phenomenologists have calculated that certain quantum gravity models, particularly those involving string theory or alternative early universe scenarios, could produce a very specific twist in the polarization of this primordial light. This twist, known as B-mode polarization at certain angular scales, would be a unique fingerprint of primordial gravitational waves, ripples in spacetime generated during the universe's first inflationary burst. Detecting this specific pattern with instruments like the Simons Observatory or future space-based telescopes would be more than just evidence for inflation. The precise statistical nature of the signal could potentially rule in or out entire classes of quantum gravity models, telling us something profound about how spacetime behaved in its first quantum tremors. The work is painstaking, often involving sifting through mountains of data for anomalies that are smaller than the most meticulous sources of noise, but it represents a fundamental change in posture. Quantum gravity is no longer purely a mathematician's puzzle. It is becoming an observational science where every distant quasar, every ancient photon, and every ripple in spacetime is a potential messenger carrying encrypted news about the unified nature of reality. Perhaps the most profound shift comes not from adding new dimensions, but from rethinking what reality is made of. What if the fundamental substance of the universe is not matter, not energy, not even spacetime, but something far more abstract: information? This is the information theoretic perspective, a viewpoint that asks us to see the cosmos not as a collection of things, but as a vast, dynamic computation. The seeds of this idea were planted decades ago by the visionary physicist John Archibald Wheeler, who coined a deceptively simple phrase, "it from bit." For Wheeler, every particle, every field, every tick of time ultimately derives its existence from binary answers to yes or no questions, from bits. In this radical view, the physical world, the it of matter and force, is not primary. It emerges from the bit, from the immaterial processing of information. The universe is not a machine made of gears and levers. It is more akin to a cosmic computer, and the laws of physics are the software it is running. This perspective finds startling support in the holographic principle we explored earlier. Remember, the holographic principle suggests that all the information describing a three-dimensional volume is encoded on its two-dimensional boundary. This is a literal, physical realization of it from bit. The rich, three-dimensional world we experience with its galaxies and oceans is not the fundamental data. It is the projection, the rendered image, generated from a deeper layer of information painted on the cosmic horizon. The it of our reality emerges from the bits stored on that distant surface. This idea connects powerfully to another quantum phenomenon, entanglement. When two particles become entangled, they share a single quantum state, no matter how far apart they are separated. A measurement on one instantly determines the state of the other, a spooky connection that Einstein famously disliked. But in modern physics, entanglement is not a bug. It is a fundamental feature, a kind of quantum information link. Recent research has pushed this connection to a breathtaking extreme, leading to a tantalizing conjecture known as ER equals EPR. This proposal, developed by thinkers like Juan Maldacena and Leonard Susskind, suggests a direct link between two concepts that seemed utterly unrelated. ER refers to Einstein-Rosen bridges, the formal name for wormholes, hypothetical tunnels through spacetime connecting distant points. EPR refers to Einstein-Podolsky-Rosen, the trio who first highlighted the strange paradox of quantum entanglement. The conjecture boldly proposes that these are two sides of the same coin. The mysterious, instantaneous connection of entangled particles, EPR, might be physically described by a microscopic wormhole, an ER bridge, linking them through the fabric of spacetime. In other words, quantum entanglement and the geometry of spacetime are not separate phenomena. They may be one and the same, described in different languages. This leads to a revolutionary picture for how spacetime itself could be built. Imagine the universe's fabric not as a pre-existing stage, but as a web of countless quantum entanglements between fundamental degrees of freedom. Where entanglement is strong and complex, spacetime emerges as a smooth, connected geometry. Where there is no entanglement, spacetime dissolves into disconnected fragments. In this view, gravity and the curvature described by Einstein's equations are not fundamental forces. They are emergent phenomena, the thermodynamic consequence of this underlying entanglement structure, much like the pressure of a gas emerges from the collective motion of countless molecules. This offers a completely new direction to derive gravity from quantum principles. We are no longer trying to force gravity into the quantum rulebook. Instead, we are discovering that the rulebook of quantum information and entanglement, when applied on a vast scale, naturally generates the stage of spacetime and the force of gravity as a consequence. The search for quantum gravity becomes a search for the rules of this cosmic quantum network. It suggests that when we finally peer into the heart of a black hole or the first moment of the Big Bang, we may not find a singularity of infinite density, but a transformation of information, a moment where the quantum connections that weave spacetime together reconfigure themselves into a new pattern. Yet this vision of a universe built from information leads us to a paradox even more fundamental than singularities or infinities. Time itself, the very river of change we all experience, might be an illusion. This is the problem of time, and it strikes at the heart of every attempt to merge quantum mechanics and gravity, revealing a conceptual chasm so deep it questions the nature of reality. In our everyday world and in all of quantum mechanics, time is the ultimate stage manager. It is an external, absolute background against which every event unfolds. Particles oscillate, atoms decay, and waves evolve, all measured against this independent, flowing parameter. Time is the conductor, and the quantum orchestra plays to its steady, unyielding beat. But step into the universe described by general relativity, and time undergoes a radical transformation. It is no longer a separate conductor. It is one of the musicians woven inseparably into the four-dimensional fabric of spacetime. Gravity warps time as surely as it warps space, causing clocks to tick at different rates near a planet or a black hole. Here, time is dynamic, relative, and deeply entangled with geometry. The problem arises when we try to apply the quantum rulebook to gravity itself. In a key approach called canonical quantization, physicists take Einstein's equations and try to promote them to quantum operators, much like they did for the other forces. But when they do this, something startling happens. The most important equation they derive, known as the Wheeler-DeWitt equation, seems to describe a universe that is completely frozen. The variable for time simply vanishes from the equation. It is as if the quantum description of the entire cosmos yields a single, timeless snapshot, a static block with no before or after, no evolution, no change. This is not a mathematical error. It is a direct consequence of treating the whole universe as a quantum system. In general relativity, the geometry of spacetime tells matter how to move, and matter tells spacetime how to curve. There is no external clock sitting outside the universe to measure progress. When you quantize this self-contained system, the concept of an external time parameter has nowhere to come from. The theory appears to describe all of history from Big Bang to heat death in one single, eternal now. This is profoundly at odds with everything we experience. We remember the past, anticipate the future, and watch stars be born and die. How can a fundamental theory of reality have no place for this undeniable flow? Different approaches to quantum gravity tackle this chilling puzzle in radically different ways. One prominent strategy is to find time within the frozen picture. Perhaps time is not a fundamental ingredient but an emergent property, a story we tell about correlations between changing things. Think of a movie. The film strip itself is a static sequence of frozen frames, but when light shines through it at the correct speed, the illusion of motion and time emerges. In a similar way, our experience of time might emerge from the changing relationships between physical degrees of freedom within the timeless quantum state of the universe. One component, like the overall size or scale of the cosmos, could serve as a clock. As the universe expands, other things change relative to it, creating the appearance of a sequence. In loop quantum gravity, for instance, the spin network evolves not in an external time, but through a sequence of discrete steps, like the ticking of a fundamental quantum clock. Our familiar, smooth flow of time would be a large-scale approximation of this underlying granular progression. String theory and the holographic principle offer another angle. In the AD-SCFT correspondence, time on the boundary of the universe is well-defined and ordinary, part of the quantum field theory that lives there. The emergent gravitational time in the bulk interior is a projection of that boundary time. Time, in this view, is a holographic illusion generated by the dynamics on the cosmic edge. The most radical interpretations come from the information theoretic perspective. If reality is fundamentally a network of quantum information and entanglement, then what we perceive as the flow of time might be the processing of that information, the updating of correlations across the cosmic network. The past is a record of one configuration of data, the future a set of possibilities, and the present is the moment of computation. Each of these resolutions carries a profound philosophical weight. They suggest that the passage of time, with its poignant sense of loss and anticipation, may be the most convincing and persistent illusion of all, a story written by the universe to make sense of itself. The problem of time forces us to ask not just how gravity works, but what it means for anything to happen at all. This timeless view of reality forces us to confront the most intimate moment in quantum mechanics, the act of measurement itself. In our everyday world, objects have definite properties. A chair is either here or there, but in the quantum realm, particles exist in a haze of possibilities, a superposition of states described by a wave function. They are, in a very real sense, both here and there, spinning in two directions at once until the moment we look. Then, mysteriously, the wave function collapses. The particle snaps into a single, definite reality, and we get a concrete measurement. This is the infamous measurement problem. What or who causes this collapse? Is it the consciousness of the observer? Is it the interaction with a macroscopic instrument? The standard quantum textbooks offer no fundamental answer, treating collapse as an external, almost magical rule tacked onto the theory. But what if this quantum strangeness is not separate from gravity at all? What if the very collapse of the wave function, the transition from fuzzy probability to sharp reality, is orchestrated by the gentle, universal pull of gravity itself? This is a speculative but profoundly compelling frontier. The idea suggests that the two great mysteries of modern physics, the quantum measurement problem and the nature of gravity, might be two sides of a single, deeper coin. One of the most famous proposals along these lines comes from the minds of physicists Lajos Diossi and later, the renowned Roger Penrose. Their conjecture is deceptively simple, yet its implications are universe-shaking. They propose that gravity, or more precisely, an object's own gravitational self-energy, is what ultimately causes quantum superpositions to collapse. Here is how it might work. Imagine a single particle, like an electron, in a superposition of being in two different locations at once. According to standard quantum theory, this can persist indefinitely. But according to the Diossi-Penrose idea, this situation is fundamentally unstable because of gravity. Each possible location of the particle corresponds to a slightly different curvature of spacetime. The superposition is not just a particle in two places, it is spacetime itself in two slightly different configurations. Maintaining this split in the fabric of reality requires energy. Penrose argues that this gravitational superposition has a kind of energy uncertainty, and like all unstable quantum states, it will eventually decay. It will spontaneously choose one configuration over the other, collapsing the wave function. The key point is the scale. For a tiny particle like an electron, the gravitational differences are so minuscule that the superposition could last for astronomical lengths of time. But for a larger object, say a grain of sand or a cat, the different spacetime curvatures become significant. The superposition becomes incredibly short-lived, collapsing almost instantly into a single, definite state. In this picture, there is no need for a conscious observer. Gravity itself acts as the ultimate observer, constantly monitoring the mass distribution of objects and forcing anything sufficiently large to behave classically. This provides a potential, natural solution to the measurement problem. It also forges a direct physical link between quantum indeterminacy and the geometry of spacetime. The fuzzy probabilities of the quantum world are incompatible with a single, well-defined spacetime. Gravity, as the curator of spacetime, cannot tolerate this ambiguity for large masses and resolves it by forcing a definite outcome. This is more than philosophical elegance, it makes a testable prediction. If gravity causes collapse, then we should be able to detect the very faint, spontaneous radiation that such collapse events would produce, a kind of whisper of noise in the universe. Experiments are now underway with exquisitely sensitive instruments, like tiny, super-cold vibrating membranes or optically levitated nanoparticles, trying to listen for this signature. They are attempting to put ever larger objects into quantum superpositions, to see at what mass scale gravity might intervene and force a classical reality. Another fascinating connection emerges when we consider entanglement, that spooky quantum link. If gravity is indeed the mechanism that localizes objects into definite positions, then it might also play a role in limiting how far entanglement can spread in systems with significant mass. The geometry of spacetime, warped by mass, could naturally sever or constrain these quantum connections, weaving the classical world directly out of the quantum tapestry. While these ideas remain highly speculative, they represent a thrilling direction. They turn the problem on its head. Instead of struggling to quantize gravity, they explore how gravity might quantize the world. They suggest that the peculiar rules of the quantum realm, which seem so detached from our daily experience, might in fact be a direct consequence of the universe's most familiar force, quietly shaping reality at every scale. Yet beyond these established camps, the search for unity has also inspired a wild garden of radical alternatives. When the well-trodden paths seem to lead to impasses, some of the most brilliant minds in physics have dared to start over, building new visions of reality from entirely different foundations. These speculative ideas are not fringe curiosities. They are vital signs of a field in ferment, a testament to the raw intellectual courage required when your map runs out and you must sketch a new one from pure imagination. One such radical departure comes from the mind of computer scientist and entrepreneur Stephen Wolfram. His physics project is built on a deceptively simple premise that the universe is not governed by continuous equations at all, but by discrete computational rules. Imagine reality as an immense cellular automaton, like a cosmic version of the game of life, unfolding on a vast, abstract grid. At each tick of a fundamental clock, simple rules update the state of each cell based on its neighbors. From this relentless, mindless computation, Wolfram argues, all the complexity of physics, from the motion of planets to the laws of quantum mechanics, could emerge as large-scale patterns. In this view, spacetime, particles, and forces are not primary. They are approximate descriptions of the complex behavior generated by the underlying code. It is a vision of the universe as the ultimate emergent program, where even our most cherished physical laws are just recognizable regularities in the output of a deeper, algorithmic process. A different, equally provocative idea comes from theoretical physicist Eric Verland. He proposes that gravity is not a fundamental force of any kind. Instead, it is an emergent phenomenon, a consequence of entropy and the way information is organized in space. This idea, called entropic gravity, draws a direct line from the thermodynamics of black holes to the force we feel every day. Verland's starting point is the holographic principle that information about a region of space resides on its boundary. When ordinary matter enters such a region, it displaces this foundational information, increasing the entropy on the boundary. Nature, seeking to maximize entropy, responds by moving boundaries to accommodate this change. From our perspective within the space, this adjustment of information boundaries manifests as an attractive force, gravity. In this breathtaking leap, the pull of Earth, the orbit of the Moon, and even the observed effects we attribute to dark matter could all be traced back to the universe's innate tendency toward disorder and the way it stores data. It is a theory that demotes gravity from a cosmic architect to a thermodynamic side effect, a cosmic illusion born from information processing. Another deeply mathematical avenue explores the geometry of reality at the quantum level through a framework known as non-commutative geometry. Pioneered by mathematician Alain Connes, this approach suggests that at the Planck scale, the very concept of a point in space loses meaning. In our familiar world, you can measure the position of an object along different axes and get answers that are independent of the order. Measuring left-right and then up-down gives the same result as up-down then left-right. The measurements commute, but in the fuzzy realm of quantum gravity, Connes proposes, this may no longer be true. The coordinates of spacetime might become non-commutative, like the position and momentum of a quantum particle. You cannot precisely specify both at once. This fundamental fuzziness implies that spacetime at its core is not a smooth manifold, but a more abstract quantum mathematical structure. From this algebraic starting point, researchers have shown that the entire standard model of particle physics, with its intricate symmetries and forces, can be derived almost miraculously from the geometry of this non-commutative space. It is an approach that seeks unity not by adding ingredients, but by changing the very mathematical language we use to describe the stage of reality itself. These outsider ideas and others like them are often met with healthy skepticism. They are highly speculative, difficult to test, and far from complete. Yet their very existence is crucial. They serve as intellectual pressure valves, challenging the assumptions that have hardened within the mainstream. They remind us that the ultimate answer might not look like a more complex version of what we already know, but could be something we have not yet learned how to see. In a quest as profound as this, the willingness to entertain radical paradigms is not a sign of desperation, but of vitality, a recognition that the universe owes us no obligation to conform to our current aesthetic or mathematical preferences. A century of searching for a single, final theory has not given us the simple answer we hoped for, yet this long and winding road has been anything but a failure. It has been a masterclass in scientific discovery, teaching us profound lessons not just about the universe, but about how we must think to understand it. The first and most humbling lesson is the sheer depth of the problem itself. We began with the naive hope that we could simply add gravity to our existing quantum rulebook, a straightforward extension of a winning formula. The violent mathematical infinities that greeted us were not a sign of a flawed calculation, but a flashing red light, a warning that our very assumptions about reality were incomplete. This conflict forced us to realize that gravity is not just another force. It is the geometry of the stage upon which all other forces perform. Trying to quantize it like the others is like trying to describe the rules of a play while ignoring the theater, the lighting, and the fact that the actors are building the set as they go along. The problem's depth demanded a new kind of thinking, a willingness to question the bedrock concepts of space, time, and substance. In response, our mathematical toolkit has undergone a quiet revolution. To navigate these new ideas, physicists have had to become architects of unimaginable shapes. The language of simple calculus and differential equations, so powerful for planets and particles, proved inadequate. We had to learn to speak in the tongues of higher dimensional geometry and topology, the study of shapes and their properties that do not change when you stretch or twist them. Concepts like Calabi-Yau manifolds from string theory are not just abstract curiosities. They are precise vocabularies for describing how 6 hidden dimensions could curl into a stable, particle-generating shape. The spin networks of loop quantum gravity are a new grammar for constructing space itself from discrete quantum links. This journey has turned theoretical physics into a kind of exploratory mathematics, where inventing a new geometric concept can be the first step toward describing a new facet of reality. Perhaps the most beautiful lessons have come from the unexpected bridges built between seemingly distant kingdoms of physics. The most startling of these is the deep, now undeniable connection between gravity and thermodynamics, the science of heat and disorder. It began with the realization that black holes have entropy, a measure of hidden information proportional to their surface area. This hinted that the most gravitationally extreme objects in the universe obey the same statistical rules as steam in an engine. This link blossomed into the holographic principle, suggesting that all the information in a volume of space is painted on its boundary, merging the laws of gravity with the laws of information processing. Then came the astonishing proposal that quantum entanglement, the spookiest feature of the subatomic world, might be physically woven into the fabric of spacetime through microscopic wormholes. These connections are not convenient analogies, they are mathematical equivalences, screaming that gravity, thermodynamics, and quantum information are different faces of a single, deeper truth. We went looking for a theory of quantum gravity and discovered that the universe might be, at its heart, a vast and dynamic quantum computation. So has this century-long quest been worthwhile without a final answer? Absolutely. It has reshaped our conception of reality more fundamentally than any single discovery could. we no longer see space as a passive container or time as a universal river. We see a dynamic, emergent, and possibly discrete geometry that might be born from quantum relationships. We no longer see gravity as merely a force that pulls apples from trees. We see it as a thermodynamic force, a holographic projection, or the collective behavior of spacetime's fundamental threads. The search has been scientifically fruitful beyond measure, spinning off new insights into condensed matter physics, quantum computing, and cosmology. It has taught us humility before the cosmos's complexity and courage in the face of its mysteries. The final theory, if it exists, will not be the end of the story. It will be the new language we learned from this long, magnificent struggle, a language finally capable of telling the whole tale. The final theory may still be out of reach, but the tools to find its first clues are now being built. This is the dawn of an observational era for quantum gravity, where new generations of instruments will scan the cosmos with a sensitivity that borders on the miraculous. The coming decades will see our silent universe begin to speak in a language we are finally learning to hear. At the forefront are the next generation of gravitational wave observatories, designed to listen to the quietest ripples in spacetime. The Laser Interferometer Space Antenna, or LISA, is a revolutionary mission set to launch in the next decade. Instead of detectors on Earth, it will consist of 3 spacecraft flying in a vast triangular formation, millions of kilometers apart, connected by laser beams. This will create an interferometer of staggering scale, sensitive to gravitational waves at much lower frequencies than ground-based detectors can perceive. LISA will hear the gentle hum of millions of binary stars in our galaxy, the stately mergers of supermassive black holes at the hearts of distant galaxies, and even the faint whispers from the very earliest moments of the universe. It is in these exotic signals that theorists hope to find anomalies, perhaps a faint echo or a ring-down distortion that betrays the quantum structure of an event horizon, a direct signature of physics beyond Einstein's smooth predictions. On the ground, projects like the Einstein telescope and Cosmic Explorer envision detectors with arms 10 times longer than current facilities, buried deep underground to eliminate seismic noise. Their unprecedented sensitivity could catch the detailed gravitational wave fingerprint of a neutron star collapsing into a black hole, a process where quantum gravity effects might leave a subtle but detectable imprint on the final chirp. Eyes will also turn upward to the ancient light of the cosmic microwave background with a new level of precision. Next-generation observatories like the Simons Observatory in Chile and the proposed CMB Stage 4 experiment will map the temperature and polarization of this primordial glow with microscopic detail. They will hunt for the specific swirl patterns, known as primordial B-mode polarization, that are the unique signature of gravitational waves generated during cosmic inflation. Finding this signal is a primary goal, but the real treasure may be in the statistics. Does the pattern of these swirls or the distribution of the temperature spots show a subtle deviation from the predictions of standard inflation? Such a deviation could be the fossilized imprint of quantum gravity at work in the universe's first fleeting instance, a direct snapshot of spacetime being born from a quantum foam. Alongside these grand cosmic endeavors, advanced particle detectors continue to push the boundaries. The Large Hadron Collider may be joined by even more powerful machines, or we may find more ingenious ways to use it. Scientists are developing ultra-precise atomic clocks and matter-wave interferometers that can measure the tiniest deviations in the flow of time or the behavior of quantum superpositions. These tabletop experiments search for the minute blurring or noise that would appear if spacetime has a granular texture, testing models like the Diosy-Penrose objective collapse idea by trying to put larger and larger objects into quantum states to see if gravity itself steps in to enforce classical reality. This flood of new data will be meaningless without a revolution in theory to interpret it. This is where the profound insights from holography and entanglement become not just philosophy but practical tools. The holographic dictionary, translating gravitational problems into quantum information problems, provides a powerful new way to generate testable predictions. Theorists can use it to calculate what specific, observable signatures exotic quantum gravitational states, like fuzzballs or firewalls at black hole horizons, would produce in gravitational wave signals or in the light bending around a black hole's shadow. The study of entanglement entropy and its connection to spacetime geometry offers new ways to model the early universe, making concrete forecasts for what patterns we should, or should not, see in the cosmic microwave background if spacetime emerged from a quantum network. The convergence is clear. We are no longer staring at a blank chalkboard. We are preparing to receive a cosmic data stream, and for the first time, we have sophisticated theoretical frameworks capable of asking it specific, pointed questions. We can ask the data if black holes have hair, if time is fundamental, or if the universe's constants are truly constant. The next great breakthrough may not be a single eureka, a moment from a lone genius with a pen, but a slow, collective deciphering of a faint signal picked up by a machine listening to the echoes of colliding black holes or seeing a peculiar twist in the light from the edge of time. The long search is entering its most promising chapter, one where the universe's deepest secrets are no longer locked in pure thought, but are waiting, encoded in the gentle ripples and the ancient light, for our machines and our minds to finally understand. This immense effort compels a deeper question, one that goes beyond equations and experiments. What exactly are we searching for when we seek to unify physics? Is the fabled theory of everything meant to be a single, elegant equation carved into a cosmic tablet, the final and complete description of nature? Or is it something more flexible, a consistent framework, a set of principles that allows us to calculate what happens at any scale we can probe? This distinction is not just semantics. It defines the very soul of the quest. For centuries, physics has progressed by finding deeper, more fundamental layers of reality. Atoms were built from protons and neutrons, which were built from quarks. This reductionist dream suggests that if we just keep digging, we will eventually hit bedrock, the ultimate set of indivisible building blocks and the simplest possible laws governing them. The search for a single, final equation is the purest expression of this dream. It is the hope for a universe that is, at its heart, perfectly knowable and elegantly simple. Yet our journey through these theories suggests a different possibility. Perhaps the universe is not structured like a set of nested Russian dolls, with one ultimate truth at the very center. Perhaps it is structured more like language. Consider the relationship between the microscopic world of chemistry and the large-scale world of biology. You cannot understand the breathtaking complexity of a living cell, its ability to replicate and adapt, by only studying the quantum mechanics of its individual carbon and hydrogen atoms. At each new scale of complexity, new laws and principles emerge that, while perfectly consistent with the rules below, are not reducible to them. They have a life of their own. In this view, a theory of everything might not be a single master equation from which all else is derived. It might instead be a perfectly consistent and seamless framework, a kind of cosmic dictionary that allows us to translate without error between the languages of the quantum world and the gravitational cosmos. Its goal would be to remove the contradictions, to provide a set of rules that work from the smallest conceivable scale up to the edge of the observable universe without ever breaking down or producing nonsense. It would be an effective theory, but one whose domain of effectiveness is all of reality. This leads to the most radical philosophical possibility of all. What if gravity itself is the signal that we have reached a fundamental limit of the reductionist dream? Our attempts to quantize gravity have all started from a deep assumption. that gravity must be brought under the quantum umbrella, that it must be broken down into discrete packets like everything else. But what if this assumption is wrong? The persistent failures might be telling us that gravity is not just another force waiting to be quantized. It might be something else entirely, a thermodynamic force, a geometric illusion, or a consequence of cosmic information processing. Unifying it with quantum mechanics would then not mean forcing it into the quantum mold. It would require a more profound revision, a new paradigm where both quantum theory and our understanding of gravity are seen as approximate, emergent descriptions of a deeper reality that we have not yet glimpsed. In this scenario, the search is not for a final equation, but for a new set of concepts, a new way of seeing that makes the old conflict simply dissolve. The long search, then, is not just a technical puzzle. It is a philosophical expedition to the very boundaries of human understanding, asking not just how the universe works, but what it even means for something to be fundamental. A century of searching has not delivered the simple, final equation some dreamed of, but it has gifted us something far richer, a transformed understanding of reality itself. We set out to heal a single fracture in our cosmic map, the war between the quantum and the gravitational, and in doing so we discovered that the map was far stranger than we ever imagined. We now see a universe that might be woven from vibrating strings dancing in hidden dimensions, or from a dynamic spin network of quantum geometry. We entertain the possibility that our three-dimensional world is a magnificent hologram projected from a distant, two-dimensional surface, and that the force of gravity itself could be an emergent illusion born from the universe's innate tendency toward disorder. These are not failures but triumphs of the imagination, forced upon us by the stubborn refusal of nature to fit into our older, simpler boxes. The conflict between quantum mechanics and gravity was never a flaw in our theories. It was a guidepost, a cosmic signpost pointing insistently toward a deeper layer of reality, one where space and time are not the fundamental stage but characters in a far grander story. This long search has redefined the very questions we ask. We no longer just seek to predict where a particle will be. We seek to understand what space and time are made of and how they emerge from something more primitive. The journey has woven together disciplines that once seemed separate, linking the thermodynamics of black holes to the spooky connections of quantum entanglement, and turning the entire cosmos into a laboratory for the most fundamental physics. While the ultimate unified theory remains just beyond the horizon, the path to it has illuminated the landscape around us with startling clarity, revealing black holes as cosmic laboratories and the Big Bang not as an absolute beginning, but as a profound transformation. This enduring quest speaks to something fundamental within us, a drive to comprehend the fabric of existence, to find a story that makes sense of the cosmos from its smallest whisper to its grandest echo. The search itself is the testament, a century-long conversation with the universe that has changed both the questions and the questioners. So as new telescopes peer deeper and new detectors listen more closely, we stand on the threshold not of an ending but of a new beginning. The next great revelation may come from a subtle twist in ancient light, a faint echo in a gravitational wave, or a brilliant reformulation of an idea we thought we already knew. Which of these visions of a unified reality resonates most with you? Does the elegant harmony of strings, the pure geometry of loops, or the holographic illusion feel like a glimpse of the truth? The conversation continues, and the next chapter is for all of us to discover.